On a cosmic scale, the universe is full of violent, unpredictable disorder. But zoom in, and microscopic particles operate under incredibly rigid, ordered physical laws. To understand how strict rules generate chaotic states, physicists examine electron spin. Think of an electron like a microscopic compass needle, pointing strictly up or down. Inside magnetic materials, billions of these coordinate, locking into a perfectly alternating grid known as long-range order. Under these rigid conditions, every particle dictates exactly what its neighbor is doing. Based strictly on the quantum rule set, pure magnetic chaos shouldn't have any room to exist. Yet in certain materials, that perfect grid completely collapses. The spins lock into a frozen state of seemingly random misalignment. Physicists call this broken state a spin glass. Mapping the mathematics behind this specific type of disorder is highly valuable. The exact equations that govern a spin glass are currently used by computer scientists to build modern neural networks and predict complex protein folding. But actually observing how a material enters this chaotic state has stalled for 50 years. Naturally occurring spin glasses are structurally messy right out of the ground. Because they are chaotic by default, researchers cannot observe the exact moment that chaos begins. Without a clean, highly ordered starting point, trying to trace the birth of magnetic disorder is like trying to understand a movie by walking into the theater halfway through the film. Researchers at the Okinawa Institute of Science and Technology decided to bypass this problem entirely. Instead of hunting for a naturally occurring spin glass in the wild, they set out to engineer a flawless material from scratch. Over several years of continuous refinement, the team managed to grow an ultra-pure zinc ferrite crystal. They systematically eliminated all of the natural chemical defects that usually plague the material. Once cleaned of those impurities, this custom crystal behaved exactly like a textbook magnet. It maintained pristine, unbroken long-range order across its entire structure. This flawless, uncorrupted crystal gave physicists exactly what they had been missing for half a century, an absolute blank slate. They could finally introduce chaos on their own terms. To watch the order break down, the research team needed to systematically fracture the crystal's perfect internal structure. This animated diagram illustrates their exact chemical method. They injected gallium ions into the crystal, carefully swapping them into spots previously held by iron atoms, intentionally fracturing the perfect lattice. The structural consequences were immediate. As the gallium concentration increased, sensors picked up a sharp, measurable plummet in the material's long-range magnetic order. For decades, theoretical physics assumed a specific sequence of decay. The hypothesis was that as the overall grid breaks down, these disorganized arrows would first form tight, competing groups called short-range order before finally turning into a spin glass. But the experimental data revealed a completely different sequence of events. True spin glass behavior emerged well before any of these short-range clusters formed. Exotic magnetic chaos does not grow out of frustrated group dynamics. It is driven entirely by singular, totally independent spins that have completely lost their connection to the surrounding environment. By tracking this process step by step, the research team successfully aligned 50 years of theoretical math with concrete experimental material science. And this highly controlled methodology provides physicists with a highly reliable toolkit for exploring even stranger states of matter. The next target is a phase called a quantum spin liquid. As this model shows, the individual spins never actually freeze. They remain in constant, coherent fluctuation, even near absolute zero. Mastering these constantly fluctuating states is incredibly valuable. Because they sustain a coherent pattern without locking into a static configuration, they are prime candidates for storing data inside next-generation quantum computers. It's an interesting reality of modern physics. To capture and map the universe's ultimate quantum chaos, science first had to build absolute, unbroken perfection.
Light is our fastest messenger, but when it hits a dense fog, it doesn't just slow down, it scatters into 1,000 useless directions. We see this failure everywhere we try to push the limits of optics, from the opaque layers of biological tissue to the intricate, crowded strands of multimode optical fibers. At a microscopic level, photons collide with obstacles and bounce off in random trajectories. Every collision strips away a piece of the original image until spatial information is completely lost. If you try to project a clear shape through these environments, the coherent signal hits the barrier and shatters into a field of unreadable static. This isn't a failure of our cameras, but a result of the physical world naturally scrambling data. It creates a ceiling for optical technology, limiting how deep we can see into the human body, or how far we can send data through the atmosphere. Today, researchers try to fix this using spatial light modulators, or SLMs. Think of an SLM as a high-tech funhouse mirror. It calculates the exact mess the obstacles are about to make and distorts the light in the opposite direction before it enters the medium. If perfect, the two distortions cancel out. The problem is the sheer volume of math required. To reconstruct a clear image, you must predict and reverse every microscopic bounce. In a truly chaotic environment, the data needed to keep up with these fluctuations becomes impossible to manage. We have spent decades treating chaos as an obstacle that must be overpowered with raw computing power. This makes high-resolution vision through disordered media a slow and exhausting process. Researchers at Sorbonne University and the University of Glasgow took a different approach. They realized that standard light was limited by its own physics. They looked toward quantum optics, which operates under a mathematical framework called double linearity. This provides a set of transmission solutions that are physically impossible using classical light. They began experimenting with entangled photon pairs, two individual particles of light linked together so their physical properties remain perfectly synchronized regardless of distance. By using these pairs, the team changed the mission of the SLM. It no longer spends its energy trying to reverse every collision. Instead, the modulator is optimized to do one thing: preserve the spatial correlation between the linked photons. The focus shifted from trying to protect the light beam itself to protecting the invisible mathematical relationship that connects the two particles. This works because of how light reacts to a basis change. When light enters a chaotic environment, the medium forces it to switch from an orderly layout into a disorganized physical state, a different optical basis. Imagine a standard laser beam and an entangled pair crossing this threshold into chaos. For the classical beam, this shift is fatal. Its information is tied to its original structure, which is immediately scrambled by the medium. Entangled photons are different. Their spatial correlation survives the basis change. While the individual photons might be deflected, the mathematical link between them remains unbroken on the other side. Because the quantum data lives in that relationship, rather than the beam's physical path, it survives the exact same environment that destroys classical information. This discovery reveals a strange property of disordered media. The very same physical chaos that blocks standard signals actually provides a safe passage for entangled pairs. This effectively turns the medium into a filter that discriminates between the two types of light. It swallows the classical signal, but allows the quantum information to pass through clearly. We are no longer trying to solve the problem of a disordered environment. We are turning that environment into a selective, programmable component of our optical system. This marks a shift in how we handle complex media. Chaos is no longer just a barrier to be avoided. It is a tool we can use to filter and secure information. In the world of communications, this allows for secure data transmission, where the physical environment itself acts as the shield. Any attempt to intercept the message with standard equipment would only result in noise. It also provides a way to image deep into biological tissue without the need for the massive brute force calculations that have limited medical imaging for years. The process of finding the right settings for the SLM has a secondary benefit. Calculating that perfect phase mask is mathematically identical to finding the lowest energy state in a system of multi-spin interactions. This means the experiment itself can double as an analog computer, solving complex optimization problems that are too difficult for standard digital processors. For a long time, we thought that seeing through chaos was a computational impossibility. But by utilizing quantum entanglement, we have found a way to render the most complex environments transparent. Look at this jet of plasma erupting into the cosmos. It's driven by the central black hole of galaxy Messier 87, a void 6.5 billion times the mass of our Sun.
It is one of the most energetic phenomena we can observe. This is the famous image capturing that black hole's immediate shadow. But on December 8, 2025, astronomers finally managed to map the much larger scale structure of the energy jet shooting out of it. To capture data at that scale, researchers didn't rely on a brand new satellite orbiting the Earth. They leaned heavily on an antenna housed inside a large geometric radome in Westford, Massachusetts. To map an intergalactic jet thousands of light years long, scientists had to turn to an instrument originally built on Earth over 60 years ago. This is the Haystack 37-meter telescope. It saw its first light in 1964. During its early decades, it mapped the surface of Venus and supported NASA's Apollo moon landings. By the early 2010s, however, its time on the front lines of astronomy had largely ended. The massive dish was repurposed. It became a space radar, primarily serving U.S. government agencies, leaving deep space research as a secondary, part-time activity. Before researchers could point this dish at distant galaxies again, they had to rescue it from bureaucratic retirement. Restoring the telescope's deep space capabilities required a quiet, rigorous, and exhaustive 10-year campaign led by a dedicated team of scientists. They successfully secured grants from the National Science Foundation, private donors, and MIT seed funds. Step by step, they modernized the telescope's outdated data analysis and radio signal processing hardware. The final technical hurdle was outfitting the observatory with a next-generation digital backend. They needed a signal processing system sensitive enough to capture elusive millimeter wavelengths traveling from deep space. It was a decade of tedious, unglamorous rewiring. But that foundational infrastructure work is exactly what made the stunning observations of 2025 possible. To capture a black hole jet, you need very long baseline interferometry, or VLBI. Radio waves from space strike multiple locations on Earth at slightly different times. By synchronizing these distant telescopes, their data is combined, creating a single Earth-sized dish. Here are a few of the massive dishes that make up the very long baseline array. In 2025, this network teamed up with the Greenland Telescope to observe M87. They needed an extra anchor on the eastern seaboard to sharpen the picture. The newly upgraded Haystack 37-meter telescope became that highly sensitive missing node. With Haystack online, the array successfully detected the faint outer emissions of the black hole's jet, allowing researchers to compile the first multi-frequency movies of the plasma flow. These maps trace how jets transport energy thousands of light years into intergalactic space. By observing this flow, scientists can determine how a central black hole regulates the gas supply and star formation rate of the surrounding galaxy. The telescope's new mission extends far beyond deep space. The MIT Planetary Defense Project is pointing the dish right back at our immediate cosmic neighborhood. As part of a planetary shield, researchers use radar capabilities to accurately measure the sizes and topographical shapes of near-Earth asteroids posing a hazard. Meanwhile, chemists are utilizing the dish to scan interstellar space for complex organic molecules, searching for the raw chemical precursors to life. 10 years of careful refurbishing turned a specialized radar dish back into a versatile scientific multi-tool, capable of tracking local threats and probing the origins of biology. In modern astronomy, getting time on a world-class instrument is incredibly difficult. Observation slots are fiercely protected, heavily automated, and usually reserved for senior researchers. Haystack runs on a different model. The observatory hands direct control of the multi-million-dollar instrument over to undergraduate interns. These students actively write the telescope's control systems and build the algorithms used to parse the deep space data. This program provides students with the rare technical proficiency required to operate advanced research hardware. By the time they graduate, these interns have already managed frontline observations that most astronomers only see through automated data feeds. In the local universe, galaxies and their central supermassive black holes grow in a predictable, synchronized rhythm. For decades, astrophysical models have been built on the observation that as a galaxy adds stellar mass, its central black hole paces it step for step. This diagram illustrates the remarkably consistent mass ratio we see today.
A supermassive black hole typically sits at just 0.1 to 0.5% of its host galaxy's total stellar mass. That fraction of a percent represents a predictable equilibrium. Curious, shifting tone. Then we pointed the James Webb Space Telescope into the deep field. By peering into the universe's first 1 to 2 billion years, astronomers expected to find younger versions of that same balanced system. Instead, the data revealed a disconnect that the existing models couldn't reconcile. They discovered what are now called overmassive black hole galaxies, or OBGs. These are primordial systems where the central mass relationship deviates significantly from the patterns we see in more recent cosmic history. When we apply the mass ratio to the high redshift universe, the scale tips. In these early galaxies, black holes frequently make up 10 to 30% of their galaxy's total mass. In some extreme systems, known as little red dots, the black hole mass actually exceeds the entire stellar mass of the host galaxy. This creates a physical contradiction. A black hole requires enormous amounts of time and matter to reach these proportions. If these black holes are this massive so early, we have to explain how they grew so fast while their host galaxies remained so small. The first attempt to solve this problem assumed these black holes were feeding at impossible speeds, far beyond their theoretical limits, a process known as super-Eddington accretion. But new cosmological simulations led by Mohamed Latif show that extreme feeding isn't required. In fact, their models demonstrate these massive black holes grew at half the maximum expected rate. The explanation begins before stars even existed. This visual maps out the universe's original density field, showing the very first structures to collapse, primordial dark matter halos. These acted as the gravitational scaffolding upon which the very first galaxies would form. Inside these dense structural nodes, immense pockets of raw matter bypassed the usual stellar life cycle entirely. Instead of coalescing into a star that would later die and collapse, the raw material caved in on itself, crushing straight into a singularity. This produced a direct collapse black hole, or DCBH. Because it required pristine, metal-free gas and incredibly dense dark matter scaffolding, this specific mechanism was only possible under the conditions found in the very early universe. By skipping the millions of years typically required for star formation and stellar death, these black holes secured an evolutionary head start. They were born massive, anchoring themselves long before their host galaxies had the chance to ignite their first stars. Still, a head start only explains half of the lopsided ratio. Over the next few 100 million years, the surrounding galaxy should have pulled in enough gas to form stars and balance the scale. We have to look at why the host galaxy stalled out. The direct collapse black hole actively prevented the galaxy from growing through a process called black hole feedback. As matter inevitably swirled toward the singularity, it generated intense heat and radiation, violently scattering the cool gas needed to form stars. The fraction of gas that did survive this hostile environment managed to ignite into the universe's first generation of stars, known as Population 3. These were exceptionally massive. They were incredibly bright and highly volatile. Because of their extreme mass, Population 3 stars burned through their fuel rapidly. They lived short lives that ended in extraordinarily powerful supernovae. Latif's simulations show that these stellar detonations worked alongside the black hole's own radiation. Together, the supernovae and the black hole feedback created a blowout of metals and gas, continuously heating and ejecting the remaining material, and depriving the galaxy of star-making ingredients. The math finally aligns. These lopsided ratios are the result of two simultaneous forces: a black hole that began with a massive head start in the early universe, anchored in a galaxy that was continually starved and sabotaged from the inside out. This chart compares the theoretical simulation with the physical universe. The data points you see here represent the light spectra from UHC-1 and GHC-9, two early galaxies observed by JWST. The Latif team's model plots an excellent match right through these observations. Because the numbers align closely, the simulations suggest these galaxies represent a standard phase of development for systems built around a direct collapse seed. This brings us right back to the modern local universe we started with. billions of years of cosmic time have allowed those host galaxies to accumulate enough mass to eventually reach the mass ratios we see in our neighborhood today. The predictably sized supermassive black holes anchoring our modern galaxies likely exist because these ancient direct collapse singularities served as their foundational seeds. The anomalies James Webb captured in the deep field didn't overturn the laws of physics. They provided the first look at the earliest epochs of cosmic history, revealing the violent construction of the universe's gravitational backbone. When astronomers look out into the deep cosmos, they see galaxies rushing away from us faster every day. We call the invisible driver of this accelerating expansion dark energy. Since the time of Albert Einstein, physicists have largely modeled this energy as a steady, unchanging pressure pushing the universe apart, the cosmological constant. Recently, however, the DESI collaboration reported findings that suggest dark energy's equation of state might not be a fixed number, but something that shifts as the universe ages. If the strength of dark energy isn't a constant, then the simple, steady universe we've modeled for decades no longer fits. It would mean our current math for the trajectory of the cosmos is built on a premise that may not hold up. The problem is, dark energy is invisible. We can't observe it directly. We can only infer its properties mathematically by studying massive, incredibly complex datasets. When a dataset suggests a conclusion that alters our basic understanding of physics, the methodology has to be flawless. We have to know if DESI's measurements are truly robust. Before we move away from our established models, we have to audit the raw data that generated this new claim. That is exactly what researchers Samsuzaman Afroz and Suvodeep Mukherjee set out to do. They decided to stress test the evolving dark energy claim by pitting its foundational datasets against each other. The first dataset acts as a cosmic ruler. We use the blinding explosions of distant supernovae as standard candles, measuring how fast they move away. The second dataset measures baryon acoustic oscillations, or BAO. These are ancient, frozen ripples in the density of visible matter, generated by acoustic waves in the primordial plasma right after the Big Bang. While supernovae and BAO track the exact same universe, they calculate distance using completely independent methods. That makes them perfect tools to cross-check one another. To perform this cross-check, Afroz and Mukherjee needed a control variable, a foundational rule that holds true under general relativity. They found it in something called the cosmic distance duality relation. This diagram models how the rule works. If you have two independent tools measuring the exact same cosmic distance, they must intrinsically connect. Their mathematical results must synchronize completely. Therefore, if the measurements pointing to evolving dark energy are sound, the underlying datasets must perfectly satisfy this duality relation. The team ran the massive supernova datasets and the DESI BAO measurements through the duality test to see if they matched. At first glance, they are broadly consistent. But looking closely, this graph shows the two lines separating, a minuscule mismatch. As we scale out to the universe's edge, this tiny error widens, drastically distorting our timeline of cosmic expansion. If the foundation is misaligned, any complex calculations built on top of it will be skewed, including the behavior of dark energy. Afroz and Mukherjee then mapped the precise size and shape of this data mismatch directly onto the DSI parameters that first suggested dark energy was evolving. The anomaly perfectly correlates with the systemic error. The evolution we thought we saw isn't a physical change in the cosmos, it is a discrepancy inside the instruments themselves. The researchers concluded that the evidence for dynamical dark energy is effectively absent. The classic steady cosmological constant remains our most accurate model. What initially looked like a shift in the laws of physics was actually a phantom signal, born entirely from microscopic misalignments in the raw data. Astrophysics is rapidly entering an era dominated by massive observatories, gathering volumes of information far beyond what human beings can manually parse. Afroz and Mukherjee's auditing technique provides a critical blueprint. Moving forward, teams will use it to estimate and mitigate these hidden systematic effects in upcoming surveys. Until those tools are flawlessly calibrated, it is too early to claim a robust detection of dynamical dark energy. Unlocking the nature of dark energy depends on our ability to guarantee that the foundational data is sound. When you look at the Milky Way, Star clusters are broken up by dark, cloudy bands cutting through the center of our galaxy. That cloudiness is actually vast amounts of cosmic dust, creating a massive blind spot in our night sky. Because of that dust, about half of the light coming from the galaxies in our universe is completely hidden from view. This creates a scientific roadblock known as the confusion limit. To understand it, look at this diagram. When observing deep space, distinct light sources from far-off galaxies hit that dust layer and smear together into a single glowing smudge. Because of that blurring effect, astronomers run into a wall. They can detect the light, but they cannot tell if that single smudge is coming from one massive galaxy, 10 smaller ones, or 1,000 of them clustered together. Currently, our best tool for peering through that dust is the ALMA array, a collection of 66 radio antennas positioned in Chile's Atacama Desert. But ALMA has a strict mechanical limitation. It acts like a high-powered microscope. In any given observation, it can only see an area of the sky thousands of times smaller than the surface of the moon. You cannot map the entire sky using a microscope. Relying on such a narrow field leaves us with a biased picture, missing half the universe without a wide enough lens. To fix that blind spot, a new European-led coalition is returning to that high, dry, and pristine atmosphere in the Atacama Desert. They are designing the Atacama Large Aperture Submillimeter Telescope, or ATLAST. If ALMA is a microscope, ATLAST is a wide-angle camera, engineered to capture submillimeter radiation across the whole sky. This scaled outline shows exactly what it takes to get that wide-angle view. ATLAST requires a 50-meter primary dish and a 12-meter secondary mirror. The entire steel and aluminum structure will weigh roughly 4,400 tons. Despite weighing as much as a freight train, that entire structure has to move, sweeping back and forth across the sky incredibly fast to actively map the sky. By combining that massive surface area with high-speed sweeping, a single ATLAST observation will capture an area 16 times the size of the moon. The microscope limitation is entirely eliminated. But building a 4,400-ton machine creates an immediate engineering problem. How do you run a power-hungry, high-speed observatory in a remote, high-altitude desert without relying on fossil fuels? The engineers solved this by designing the telescope to run like a giant hybrid car. As the dish slows from a sweeping motion, it brakes, recovering kinetic energy as electrical charge for an onboard battery bank. This energy is combined with solar power and metal hydride storage to create a self-sustaining grid tailored to its movements. The project even plans to use near-zero carbon power to manufacture the raw steel and aluminum needed for the dishes. The researchers hope this design sets a pattern for future megascience, showing that even a power-hungry 50-meter class observatory can operate within the limits of Europe's climate targets. With the power and mechanics sorted, the focus shifts back to the sky and to the data this wide-angle lens will actually capture. By tearing through the confusion limit, astronomers project ATLAST will uncover up to 50 million previously hidden galaxies in just 1,000 hours of observation. Mapping those missing galaxies allows researchers to locate the vast reservoirs of cold gas and dust that act as the raw fuel for star and planet formation. By peering into the debris disks surrounding young stars, the telescope will also be able to spot specific molecules, giving us a direct look at the chemical building blocks of life as they form. Plotting 50 million new data points across the sky gives physicists the density maps they need to measure the gravitational pull of dark matter and to calculate the accelerating expansion of the universe driven by dark energy. And unlike disposable tech, ATLAST is designed to do this long-term. The facility features an upgradable instrumentation bay to keep it operational for at least 50 years. Linking what our other giant observatories see to this new map of cold gas and dust, ATLAST provides the data needed to observe the full evolution of galaxies across cosmic time.